You didn't wake up this morning 'cause you didn't go to bed, watching the whites of your eyes turn red. It's a good song, and this is going to be a good video, I think, because the room smells of sick. Because someone was sick in here, and no one's came here to fucking sort it out. Welcome back to your 4th essential chemistry video. Today we'll be talking about bonding in compounds. But what the hell's a bloody compound, Paul? Like, just to recap, if you didn't see the third video, which you probably should see, because we talk about important things actually, so I don't know what you're playing at. Like, not even fucking seeing the video for you fucking... An element, when we talk about an atom being an element, we're talking about an atom with a certain number of protons. So all atoms in the nucleus. So all atoms that have 6 protons in the nucleus are called carbon. All atoms with 1 proton in the nucleus only are called hydrogen. With 10 protons in the nucleus only, they're called neon. When you talk about a molecule being an element, it's just made of, one element. So a hydrogen molecule is just 2 hydrogen atoms. When you talk about a substance, made of many molecules, being an element, it's just that element it's made of. So hydrogen gas is just hydrogen molecules, which is just hydrogen atoms. A compound, by contrast, is a substance made of more than one type of element. So water is a good example. Water, I'll do your water molecule right now. This is a compound that's made of 1 oxygen atom and 2 hydrogen atoms. You can have something like methane, which is just CH4. Fucking methanol. I'm not quite sure if I'm drawing the organic chemistry nomenclature right there, but screw it. Of course, it can be any 2 or more elements. Doesn't just need to be oxygen, hydrogen, and carbon. Those are the only ones I know because I done a lot of organic chemistry in college, and I still have the nightmares. But last time, we covered bonding in elements. Again, see that. I'd see that first, unless you're already familiar with bonding in elements. Because we covered a lot of that stuff will be here as well. And I think from my experience, if you're being very cocky around a subject for an exam, the amount of times I've been cocky about a subject and I just fucking know nothing about it. Like, I was taking my chemistry exams, I thought I knew it, got a fucking C in the final exam because I was too cocky about it. Let's see. Yeah, we covered stuff like pure covalent bonds last time. So this E stands for elements, this C stands for compounds. Do pure covalent compounds occur in elements? They absolutely do. Do they occur in compounds? Yeah, they do actually. Because remember, when two or more atoms, well, actually, it'd be 2 atoms in a covalent bond. When the electronegativity, which, if you didn't know what that is, well, you should watch the last video. If it's less than 0.5, it's a pure covalent bond. So any 2 compounds have similar electronegativities, like carbon and hydrogen, Paul. It's just pure covalent bond. So yeah. We also covered London dispersion forces. That's what LDF stands for. It occurs in both elements and compounds. Every atom's got where is the remote? That's what you get for recording these videos in your fucking house. An electron cloud, every atom has an electron cloud around it, and fluctuates. Some areas will be denser sometimes in the cloud, some will be lighter, so that the denser areas will have a slight negative charge, the lighter areas will have a slight positive charge. These are temporary, so of course these are going to happen in the compounds as well. If you didn't know that, if you watched that third video, metallic bonds. We do like a good metallic bond here on this channel. Yep, in elements, yep, in compounds. Look it up if you want to see a compound metal. Because I don't know any. I'm not brave enough to see any. Because I'm just like, I've just left college. I'm not a college professor or teacher, but I do research these videos. I do curriculum, so I'd see a bit more, maybe use more than my videos, or use some other videos, use textbooks if you're revising, because yeah, I'm pretty much in the same position as you, if you're in high school, that is. Well, I'm not in high school, but oh well. But that's it for the ones that we covered last time. But what about this time? Well, actually, before we get on to that, last video I forgot to mention some things about covalent bonds. They're cool. And that's it. No, there's different types. I don't know. I can't remember if I mentioned them actually. Forget, even if I'll go over them again. You can have single bonds, like with hydrogen here. You just share one pair of electrons between the two atoms. You can have double bonds, like in oxygen. I should probably just do the dot cross sort of notation. Where you share two pairs of electrons each. Or you can have a triple bond, like in a nitrogen molecule. And how you'd draw that, you can also draw it like this. Oxygen I meant. Draw it like that. Of course, these can again occur in compound arenas. Also, I should mention that. Try to keep my laptop on here. Each of the atoms in the bond don't necessarily contribute an equal amount of electrons to the bonds. If you consider carbon monoxide, which has a triple bond, well, we don't need to talk about this yet, but just a little heads up for future. Monoxide, one carbon atom, and one oxygen atom. That's what the mon means in monoxide. And the oxide just means there's a oxygen there, and there's like nothing in the beginning to indicate that there's two or more carbons there. So there's 6 pairs of electrons being shared here. And if we break that down, carbon has 4 electrons in its valence shell. Oxygen has 6. So that would be a bit hard to see, sorry. If carbon was to donate 3 bonds to the bond, it wouldn't have 8 electrons in their insertable shell. So let's just draw that now. So oxygen would have 5 left. Carbon would have 1 left. Because remember, they only share the bonds that are in the bond themselves. So let's count the number of electrons that carbon has in its shell. 1, 2, 3, 4, 5, 6, 7. This isn't how a carbon monoxide molecule is like. What happens is, right, this is a bit long-winded, but forgive me. So you've got, what do you say? Oxygen was the X's. What happens is, I should have drawn these as pairs actually instead of like this. Out of the pairs that are shared between the carbon and oxygen atom, for two of the pairs, there's one electron from carbon and one from oxygen. But for the third pair, the electrons just come from oxygen. And so what you get is that carbon's contributed only 2 electrons to the bond. And so you still have 2 in its own private shell. How many does oxygen have? 1, 2, 3, 4, 5, 6, 7, 8. And everyone wins because carbon now has 8 electrons in its shared shell and its own private shell. So 1, 2, 3, 4, 5, 6, 7, 8. And that's the magic number it fucking needs, eh? But now we're going to cover polar covalent bonds, which I'll explain what they are now. Polar covalent bonds are when the electronegativity difference between the two atoms in the bond is more than 0.5 but less than 2. So we'll get our good old friend, the water molecule. Screw you, lad. What happens is the oxygen is significant. It's got a significantly higher electron negativity value, and so the electrons are sort of pulled permanently closer to the oxygen atom. So the electron cloud around the oxygen atom is permanently denser, and around the hydrogen atoms they're permanently thinner. So the oxygen atom is permanently got a slight negative charge, while the hydrogen atoms have a slight positive charge permanently. This is different from one dispersion forces, which are temporary. So we draw a little lowercase delta, which stands for slightly negative, slightly positive, slightly positive. Pardon me! And so obviously, if you wanted, this could only occur in compounds because oh fucking baby's crying. Because in an element, in the molecule of an element, in a bond, the element's going to have the exact same electronegativity value. So, forgive the fucking baby's crying. Because yeah, they'll have the exact same electronegativity in an element, so you can have a polar covalent bond. And what happens in a polar molecule is that you have another polar molecule. Just draw this here. And I'm having a look, these fucking babies crying, huh? Oh, shut up. The slight negative ends of one molecule are attracted to the slightly positive ends of another. And so electrostatic forces form between the molecules, and they're sort of binded together. Polar covalent bonds are stronger than dispersion forces. But a difference in electronegativity above 0.5 but less than 2 is not enough. It's just not enough. It also depends on the shape of the molecule. I wonder if there's any polar bonds and any babies making too much noise to interrupt the video. Okay. Oxygen has a higher electronegativity than carbon, so it's going to be slightly positive. It's got a significantly higher electronegativity value than carbon. However, this molecule isn't polar because the negative, the positive part is lodged between two negative parts. So if, let's say another carbon dioxide molecule tries to, like the negative part tries to bond with the positive part, it'll just get repelled by the two, pulsating negative parts. It'll just be kicked away. So it depends on its geometry. So if it's a straight linear molecule like this, in terms of its shape, then it's not polar. I mean, it's got an electronegativity difference that would make it polar, but the shape just doesn't allow it. Well, with water's bent. And that's okay. That's okay. But, hey, some people are like that, but not in that way, because the negative part is away from the positive parts, so the negative part of another molecule could access this pretty easily because these are too far away from the positive part of the molecule. The war in the babies continues. But there's a special type of polar bond called, I should say, that the bond that occurs between polar molecules, like not within them but between them, this bit here, the little electrostatic force between the negative part of one polar molecule to the positive part of another, is called a permanent dipole interaction. There's a special type of interaction called a hydrogen bond. So let's see here. Just draw this. A hydrogen bond is when a hydrogen is bonded between two NOF elements. So the NOF elements are nitrogen, oxygen, and my spelling isn't too good. Fluorine, that's not how you spell it. Fluorine, you know what I'm on about. So it has to be in between any of these three elements. So in water, a hydrogen is between, well, it's covalently bonded to one of the NOF elements and has an electrostatic force or a permanent dipole interaction between another NOF element. This is a very strong permanent dipole interaction, because hydrogen has a very low electronegativity. The NOF elements have very high electronegativity. And also hydrogen bonds give some substances unique properties, which we'll get into in the next video, which is the effects bond types have on the physical properties of elements. But let's wrap up this video with one more type of bond. Ionic bonds. So, do they occur in elements? No, they don't. Do they occur in compounds? They do. This is when the electronegativity difference between two molecules in a bond is more than 2. Again, these values might vary depending on where you're learning this. Some people might say 1.7, above 1.7 is ionic. Some people might say 2. And the same goes for polar bonds. Polar molecules, or polar covalent bonds. Some people might say a difference greater than 0.5 is a polar covalent bond. Some might say more than 0.4, whatever. essentially what happens here is that one of the more electronegative atom is so strong that it just takes the electrons from the weaker one, to the point where they're not even shared. The electrons are just in the stronger atom. So let's have an example. Sodium, which is Na. I'll just draw its outermost shell. Just one electron in it. And chlorine, which is 7. I should have drawn X's, but oh well. So when they're close, this electron will just join the chlorine atom. It won't be shared between them. And you'll have a sodium ion with a complete energy shell, with a stable electron configuration, and you'll have chlorine with a stable electron configuration. An electrostatic force will form between them. So that's an ionic bond. Of course, there has to be a difference in electronegativity. This won't happen in an element, this is going to happen in compounds. But yeah, that's it for this video. Pretty easy one to do. Recorded it all on a wanna. Next video we'll be going into the effect that bond types have on a substance's physical properties. And we'll cover all the bonds that we have talked about in videos 3 and 4. Goodbye. Love you. Here are my little Spider-Man thingy slippers. Please see the description for clarifications of shit that I don't think I explained well enough. There isn't that much, but see ya, big boys.